Okay, in the last lecture we have discussed about the Verilog code for the D flip flop, and then we derived the T flip flop from the D flip flop, and then we realized a 4-bit synchronous or ripple counter. So, we will take one example of synchronous sequential circuit also, because a synchronous counter we have already discussed in the last lecture, and we will use JK flip flop to design this synchronous sequential circuits, and we will see how this JK flip flop can be instantiated to design a synchronous sequential circuit. So, I will discuss about design and implementation of synchronous sequential circuit. So, here I will take the synchronous sequential circuit as a sequence detector. Which detects 3 or more consecutive ones. In an input bit stream. So, basically this circuit will have one input where the input bit stream is coming. So, whenever the circuit detects 3 or more consecutive ones, there will be output which will becomes 1. So, how to design a synchronous sequential circuit? So, you might have studied in your digital logic course. Here I will review briefly the design procedure of synchronous sequential circuits. So, in the design of synchronous sequential circuit, the first step is obtain the state diagram. You can also call as FSM, finite state machine, from the word statement. So, here the word statement is given, you have to obtain the state diagram. So, again in synchronous sequential circuits, there are two models, one is called Mealy model, another is called Moore model. We have basically here the state logic, this basically consists of flip flops with some clock. To obtain the next state of this, we require some combinational circuit which is called as next state combinational logic. So, this basically consists of input, and also this is function of the previous state also. We know that in case of synchronous or any sequential circuit, the output is not only a function of inputs, but also on the previous outputs. This will select the next state, then the combinational circuit for CC stands for combinational circuit for output, you will get output. So, in case of Mealy model, So, the output not only a function of the states, this will give the states, here we have states, but also this is function of inputs also. This is called Meade model. Whereas, in case of Moore model, the same thing, but this particular line will not be there. If we remove this line, if we remove this, we will get this Moore model. So, the only difference between the Mealy and Moore model is, so in case of Mealy model, output depends upon the states as well as the input, whereas in case of Moore model, the output depends only on the states. Okay. So, if you see the relative advantages and disadvantages of this, the complexity of the Mealy model is normally this is less complex. Okay. But if you take the drawback, if any fluctuation occurs in the input, that will change the output also, that is undesirable one. Okay. This is the main drawback of this. Any change in input causes change in output. This is the main drawback. So, that is the reason why in most of the practical applications normally we will use Moore model, okay, where the output only function of states, is independent of the inputs. Okay. So, we will discuss here the state diagram for Moore model. So, Moore model, the output depends only on the states without regard to the inputs. Okay. So, the state diagram or FSM for this example, which detects 3 or more consecutive ones. So, I will start with a reset state which is called as S0. How to establish this S0 state? By using preset and clear signals of the flip flaps. So, the very first bit that we are going to receive from this input, if I assume that this input is x. So, the first bit can be 0 or 1, similarly second bit can be 0 or 1, like that a series of bits are coming. Okay. If the first bit received is 0, where does this state will transits, okay, where does this state goes, and when in input is 1, where does this state moves. Okay. So, we know that we have to detect 3 consecutive ones. If a 0 is detected, then it will state in S0 state only, okay, and the output will be given just below this, output will be 0. If the input is 1, it will go to the next state S1, if input is 1. This label represent input, whereas this represent output, this represent output. So, in any case the output of this S0 state is 0, because if input is 0 it states here itself, if input is 1 because the first bit, so it has not yet detected 3 or more consecutive ones, so the output becomes 0. So, coming for this S1, S1 can receive the second bit as 0 or 1. If second bit is 0, no way to detect the 3 consecutive ones, so it will simply go to the S0 state. And if 1 is received at the second stage, it will go to the next stage S2, because it can detect the 3 consecutive ones. Okay. Already 2 ones has reached, this is 1. But in any case, what is the output? 0 only, because if this first bit is in at S1, first bit is 1 at S1. Second bit can be 0 or 1, means possibility is 0 1 or 1 1. So, in any of the cases it has not detected 3 consecutive ones, so the output is 0. Now, coming for this S2 state, so if the received bit is 0, although 2 ones received, it simply goes to S0. If a 1 is received, it will go to the S3 state. but in any case, so this has received only 2 ones, okay. So either it can be 0 1 1, so this one will be 0. Because it has not yet detected third bit, okay. So where the third bit will be detected, here it is 3. So already 3 ones has reached 1 2 3. So this will be 1. Even if the fourth bit is also 1, it will stay in S3 only. So the output remains 1, okay. So if fourth bit is 0, again it will goes to the S0 state, okay. This is the state diagram of Moore model, okay. Here this output depends upon the state directly. So the state is going to decide the output. So in the denominator, whatever this value is there, that will represent the state. So if it is a Mealy model, we require only 3 states. So the complexity is less, but the drawback is any change in the input causes the change in the output. So you see the first step in the design of any synchronous sequential circuit, okay. So the second step is assign binary values to all the states. So here I am using let S0 is 0 0, S1 is 0 1, S2 is 1 0, S3 is 1 1. Then the next step is obtain the state table. So totally 4 states means we require 2 flip flops. So we will assume that this each S state is of the form of Q1 Q 0, because we require for each state we require one flip flop, okay. This is output of one flip flop, this is the output of another flip flop. So the states I am going to represent as in general, instead of writing 0 0 0 1 1 0 1 1, I will write Q1 Q 0. So where Q1 is MSB, Q 0 is LSB. So I will call as present state, PS stands for present state, Q1 Q 0. Next state not only depends upon the present state, it also depends upon the input also. So next state when x is equal to 0, input. Next state when x is equal to 1. This you can easily obtain from the state diagram, okay. So I will just redraw here state diagram. The state diagram that we have drawn in the last slide is this one, S0 by 0, S1 by 0, S2 by 0, S3 by 0. So 0 it will stay here only, 1 it will go to here, 0 it will go to the S0, 1 it will come to here, 0 it will go to S0, 1 it will go to S3, 0 it will go to S0, 1 it will stay here itself. So how to map this state diagram or FSM onto state table? So this is your input, and we can also write the output also. Output, I am assuming the output as y, output for x is equal to 0, x is equal to 1. If present state is 0 0, what is the next state? If x is equal to 0, you see here next state is 0 0 itself, x is equal to 1, next state is S1, S1 is 0 1. So, in both the cases outputs are 0 0, here also 0, here also 0. 0 1 means S1 state, when x is 0 it will go to S0 means 0 0, when s is equal to 1 it will go to S2 which is 1 0. In both the cases output is 0 0. 1 0, that is S2 state, when s is equal to 0 it will go to 0 0, otherwise when input is equal to 1 it will go to 1 1. In both the cases this is 1, this is 0 0. 1 1, when x is 0 it will go to S0, s is 1 it will remain in the 1 1 only. In both the cases 1 1 is 1 because already detected 3. Okay. So, after this stage 3 detected, so output is 1, even 4 also the output is 1. So, because this is sequence detector which detects 3 or more consecutive ones. Okay. So, if I call this output as y. So, this is a state table. Now, the fourth step is choose the type of flip flop. We can design this synchronous sequential circuits using any flip flops. So, I will take a JK flip flop. To design the circuit, but you can design using D flip flop also, T also, SR also. Okay. So, the next step is the important step which is obtaining the excitation table. So, I will take the same state table, I will take this x to the this side, so that this becomes simplified. Okay. So, I will take x q1 q0 present state, next state, because x also I have taken here, only one next state will be there, q1 q0. Same whatever the data previously it is there, I will write here. When 0 0, when x is 0, the next state is always 0 only. You see here, when x is equal to 0, so all the 4 states are 0 0 only. When x is equal to 1, the next states are 0 1 1 0 1 1 1 1. So, this is 0 0. So, in all the cases the next state is 0 0 whenever x is equal to 0. When x is equal to 1, you can see that this is 1 0 0 1 1 0 1 1 1 1, 0 1 1 0 1 1 1 1. Okay. Now, we have to write the flip flop input functions, because I have chosen JK flip flops. Here we have to write the expression for flip flop input functions. Corresponding to Q1, we have the inputs J1, K1. Corresponding to Q0, we have J0, K0. Then of course, we have the circuit output function. which is y. Y also we have already derived this one. Y is for x is equal to 0, 0, 0, 0, 1, again 0, 0, 0, 1. This is 0, 0, 0, 1, then 0, 0, 0, 1. Now, how to find out these flip flop input functions? Okay. For that we require the excitation table of JK flip flop. We know the truth table of JK flip flop is J K Q N plus 1. Zero zero, regardless of the whatever the previous state will be the next state, 0 1, this is 1, this is simply the previous state. Then 0 0 0 1, regardless of the previous state, output is 0. 1 0, regardless of the previous state, output is 1. For 1 1, whatever the complement of the previous state will be present state. This is the truth table which we have discussed in the earlier classes. Now, what is the excitation table of JK flip flop? We have derived the excitation table for D and T flip flop in a similar way. What is the excitation table of JK flip flop? So, excitation table represents the inputs required for a given change of state. So, 0 to 0, you can see here that 0 to 0 is changing here as well as here. So, what are the inputs? This is 0 0, this is 0 1. In any case j is 0, k is 0 over here, 1 here. So, it will becomes do not care, this is 0 do not care. For 0 to 1 also there are two transitions, 0 to 1 is this one, 0 to 1 is this one. So, what are the inputs? 1 0 1 1. So, 1 is j, k is do not care. Similarly, for 1 0 there are two transitions, 1 0 is this one, another is 1 0 is this one. So, what are the inputs correspond to this 1 0, this 1 0, this is 0 1 and 1 1 means x 1. Similarly, 1 1 is the remaining 1 1 are this, this is 1, this is 1. So, what are the inputs? This is 0 0 1 0. So, x 0. This is the excitation table of DF. So, this is required here because the next step is obtaining the excitation table. Now, we can see that this Q1 is changing from 0 to 0. So, for 0 to 0, what are the inputs required? 0x. So, this is 0x. Q0 is also changing from 0 to 0. So, J0, K0 is also 0x. Similarly, here you forget about the x here. So, 0 to 0 means 0x, 1 to 0, 1 to 0, 1 to 0 is x1. So, like that if we fill this one, 1 to 0 is x1, 0 to 0 is 0x, 1 to 0 is x1, 1 to 0 is x1, 0 to 0 0x, 0 to 1, 0 to 1 is 1x, 0 to 1 is 1x, 1 to 0 is x1, 1 to 1 is x0, 0 to 1 is 1x, 1 to 1 1 to 1 x0 x0. This is the important step obtaining the excitation tables. Okay. Now, the next step is obtain the simplified expressions for flip flop input functions and circuit output functions. that is the expressions for J1 K1, J0 K0 and Y in terms of the states. Okay. Now, you forget about this column. So, you have to express this as a function of the present state and x. Okay. So, what is the expression for J1? J1 is equal to, so wherever 1 is there. So, J1 is 1 here, this is 1 here. So, sigma m. So, what is this 1 corresponding to? So, this 1 is corresponding to this row. So, what is the min term? This is 1 0 1 is 5. Okay, this is min term 0 1 2 0 1 2 3 4 5 6 7. These are the min terms. Okay. So, this is 1 is min term, corresponding to this min term is 5, plus there are some do not cares also. This is do not care, which is 6, this is do not care 7, this is do not care 3, this is do not care 2. Sigma d do not cares are this correspond to 2 3 2 3 6 7. So, if you simplify this using K map, you have taken the same order x as MSB. So, x q1 I will take in the top, we can take in the bottom also. I will follow this notation 0 0 0 1 1 1 1 0 0 1. 5 is nothing but 1 0 1 is this, 2 is 0 1 0 this do not care, 3 is 0 1 1 do not care, 6 is 1 1 0 do not care, 7 is 1 1 1 do not care. So, the only possibility is we have only 2 box combination, therefore, expression for J1 is from here to here x and here q0. Similarly, you can write down the expressions for J2 K2, J0 K0. So, what about K1? Sigma m. What are the min terms for K1? This is one min term 2 3 2 3 do not cares 0 1 0 1 4 5 0 1 4 5. So, what is the expression? X q1 q2 q0 0 1 0 0 0 1 1 1 1 0 2 3 is 1 0 0 is this is one min term, 3 is 0 1 1 do not case are 0 1 0 1 4 5 1 0 0. So, K1 is simply this 4 box combination, this is x bar. Similarly, if you write for J0 sigma m, what is J0? Min term is 4 6 plus sigma d 1 3 5 7. So, if we simplify by using K map, x q1 q0 0 0 0 1 1 1 1 0 0 1, 4 is this, 6 is this, 1 3 5 7, 1 is this, 3 is this, 5 is 1 0 1, sorry this 6 is this is do not care, 5 and 7 is this. So, again we have 4 box combination, therefore, J0 is simply x. K naught sigma m, this is 1 3 5 1 3 5 plus sigma d 0 2 4 6. X q1 q naught 0 0 0 1 1 1 1 0 0 1 1 3 5, 1 is 0 0 1, 3 is 0 1 1, 5 is 1 0 1, 0 is do not care, 2 means 0 1 0 is do not care, 4 1 0 0, 6 is 1 1 0. So, we have this one 4 box combination, this is another 4 box combination. Therefore, K naught is equal to so this 4 box combination is x bar plus the other 4 box combination is q1 bar. This is equal to x q1 whole bar. So, this is the sixth step, and the last step is drawing the logic diagram. So, we have basically two flip flops. This is J1 flip flop, K1 flip flop. We have Q1 bar outputs and a clock, and this is J naught flip flop, K naught flip flop, Q naught bar. This clock will be common in case of synchronous circuits. This can be either positive edge triggered or negative edge triggered, and we have one input and an output, and the expression for the output is y is equal to, simply there are two min terms, this is correspond to x bar q1 q naught, I am not using k map because only two min terms are there, plus x q1 q naught, simply this is q1 q naught. So, the output is simply q1 q naught, as I have told in case of Moore model, the output depends only on the states, it will not depends upon the inputs. So, now we have input x. Okay. So, what are the expression that we have got? J0 is x, K0 is x q1 bar. J1 is x q0, K1 is simply x bar, and y is q1 q naught. These are the expressions that we have obtained in the last step. So, J0 is simply x. So, there is a x here which will be directly applied to the J0. This is x input, this is output. Then K0 is x q1 bar, x q1 bar is q1 is here, we are taking this q1, x we are taking here, this is K0, and J1 is x q naught, x into q naught, q naught is here, into x, this x is here, and K1 is x bar. This is x line, you have to pass through the inverter. This is the complete design of a sequence detector which detects 3 or more consecutive ones. Okay. So, here these 3 gates will form the next state logic and this will form the next output combinational logic. Okay. Now, here because we are going to use 2 JK flip flops, so in order to write the Verilog code, I will first write the Verilog code for the JK flip flop, then I will instantiate this JK flip flops twice. Okay. So, Verilog code for JK flip flop. Module JK underscore FF. For JK flip flop, we have the clock input JK inputs, output is Q. Output is Q, inputs are JK clock. Output we have to define as a register also, Q input JK clock. Always at this I have not given the bubble, so this is positive edge, pass edge clock. Now, unlike this D flip flop where output Q is equal to D, whereas here in case of JK flip flop we cannot write the output in terms of JK. Okay. Output cannot be expressed as a function of JK. So, we know the truth table that we have to implement here. So, the truth table is JK Qn Qn plus 1 0 0, or if I take the simplified truth table, this is simply Qn 0 1 0 1 0 1 1 1 Qn complement. Okay. So, here we have to take a case statement, case j comma k within flower brackets 2 bits 0 0. If jk is 0 0, then the output q will be equal to, we have to use non-blocking statement in sequential circuits. Simply q itself, that means previous and present states are same. Actually, here I will use the 2 notations, one is previous and present state. If I call this itself as a present, this will be next state. We can follow any notation, either present next or previous present. Okay. Then 2b 0 1, q will be simply 0, I will write in binary form, q is 1 bit only, 0. 2b 1 0, q is 1 bit 1. 2b 1 1, q will be q complement. End case, end module. So, this is the Verilog code for the JK flip flop. Now, to write the Verilog code for the sequence detector, okay, we can instantiate this JK flip flop code twice. Okay. So, using these relations. Module sequence underscore detector. So, for sequence detector overall we will be having one output y, one input x, another is clock. Output you can call as register y, input x comma clock, but we require 2 wires also because these are not accessible, 4 wires in fact. This is J1 is one wire, K1 is one wire, if I call the same names J0, K0, another you can call as W1, this is of course X only, this is W3, or otherwise you can take directly J1, K1, J0, K0 itself. Wire J0, K0, J1, K1, then always at X, because this clock we have embedded in JK flip flop Verilog code. Okay. Or you can directly write the assign here. So, next one is assign. What is J0? J0 is equal to X, J0 is equal to, because we will use this S X, assign J1 is equal to this is blocking statement X and Q0, assign K0 is equal to XQ1 or NAND gate. Assign K1 is equal to X bar. Assign output y Q1 Q0. Then you have to instant it. So, the name that I have given is for JK flip flop, JK underscore flip flop, JK underscore FF, I will call as flip flop 0. So, the general structure is Q, J, K clock you have to mention. Okay. Clock is common. Okay. Q becomes for 0th flip flop Q0, J0, K0 clock is same. For the second JK flip flop, if I call this one as FF1, Q1 is the output, J1 is the input, K1 is another input clock. In synchronous clock is same. Okay. This is end module. So, this is how we can write the Verilog code for the sequence detector. This is complete design and implementation. We have designed first and then we have implemented by using Verilog code. But this is actually a difficult process. For complex systems, it becomes very difficult to design using this JK flip flops or any other flip flops following the step by step procedure that I have described. Okay. So, there is a possibility to model directly the state diagram or FSM. In most of the complex systems, we will draw only the FSM. So, knowing the FSM, how to model using this FSM. or state diagrams, that we will discuss in the next lecture. Thank you.